Welcome to Unit 6. In Unit 6, we get to really start using everything we've done so far this year. It's very exciting. We finally have some applications for our derivatives and for our limits, and then we get to actually see why these derivatives are important and how we get to use them. So 4.2 is all about minimum, maximums, and critical numbers. There's quite a bit of vocabulary in this section, so I'm going to go over the vocabulary just so you have it, and then we're going to talk about what the vocabulary actually means. So absolute extrema. Let f be a function defined on the interval I if there is a number u on that interval for which f of u is greater than f of x for all x on I, then f has an absolute maximum at u. And the number f of u is called an absolute maximum value. If there is a number v for which f of v is less than or equal to f of x for all x, then f has an absolute minimum. And f of v is the absolute minimum value of f. The values f of u and f of x are sometimes called absolute extrema or extreme values. So let's talk about what this actually says. If we have a largest y, then that largest y is our absolute max. If we have a smallest y value, then that smallest y is our absolute min. When we talk about these values, even though we're comparing the y values, how this is the largest y value of the whole function, and this is the smallest y value of the whole function, we always talk about the x's. So I'd say there's an absolute min at x equals c3, and there's an absolute max at x equals b. That's a really, really important distinction. None of this is as important as understanding what we're talking about, and we compare y values, but we always talk about the x values, our independent variable. So in the last slide we went over absolute maxes and mins. We also have local maxes and mins. Sometimes the absolutes are called global, and these locals are on smaller subsections. So again, let's go over the definitions, and then I'll explain it in real words. Let f be a function defined on some interval I, and let u and v be numbers on I. If there is an open interval in I containing u, so that f of u is greater than f of x for all x on this open interval, then f has a local max or relative max at u, and the number f of u is called the local maximum value. Similarly, if there is an open interval I containing v so that f of v is less than or equal to f of x for all x on the open interval, and then f has a local minimum or relative minimum at v, and the number f of v is called the local minimum value. The term local extreme value describes either a local min or a local max. So our global here, this is the largest value in the whole entire thing. So I want to show you the difference. Let's go with red. So here's our global max, and here's our global min. But these in blue, this is the largest value of all the other values around it, and this is the smallest value of all the other values around it. This is also the smallest value of all the other values around it. So when you can be a global and a local, or you can just be a local. So now we're going to use the definitions that we've gone over to solve some problems. For each of these, we're going to find the domain, then determine where the function is continuous, then identify the absolute max and the absolute min, and then find any local extrema as well. All of these graphs are on page 289 and beyond, so if you'd like to take a look, you can follow along in your book as well. All right, figure 10. Again, that's going to be on page 290 this time. So find the domain. That's the closed interval that we're talking about. So here we start at 0, and we go until 3 pi over 2. That is the entirety of this graph exists between 0 and 3 pi over 2. Determine where the function is continuous. In this case, the graph is continuous everywhere. So we're going to say on the domain of 0 to 3 pi over 2. Find any absolute maximum value or absolute minimum value. So let's take the max for a moment. The max is right here at my endpoint. Endpoints are totally fair game for absolute values. They're not for locals, but we'll talk about that in a minute. So my absolute max is at 0, 1, and my absolute min is down here at pi negative 1. And then any other extreme values. So let's see. This is going to be a local min because it's the smallest of all the other values around it. And that's the only extreme value that we have. We don't have any local maxes. But our local min is pi comma negative 1. This is really important to note. I could say this a lot of different ways, but what I need to say, I can give it a point like I did here, or I could say f of pi equals negative 1, or I could say a local min exists at x equals pi. The x value is always super important. So either you're expressing it as a function in function notation or in a point notation. This point notation gets kind of confusing when we're talking about domain and range. So this function notation is how you're going to see me do it from here on out. All right, so with the domain, we have an open interval this time. See how these are open circles? So we're going to go from the open negative 1 to 3. So my domain is everything in between negative 1 and positive 3. And that's also where the function is continuous. I don't pick my pencil up anywhere that I go to trace this function. So negative 1 to positive 3. Let's look at our absolute max. Here is the largest y value of 1 that I have in the entire graph. So my absolute max is at f of 0 equals 1, and my absolute min is down here at f of 2 equals 7. Now let's talk about why this isn't an absolute min. It's not an absolute min because it's an open circle, so that point doesn't exist within the domain. Additionally, we have our local max, which is also f of 0 equals 1, and our local min, which is also f of 2 equals negative 7. Forgot the negative. So let's look at our domain for this one. It looks like I get close to negative 1, but I have an asymptote at x equals negative 1. So I'm going to have an open interval on the negative 1 side, and I come to a point at 4, so that's a closed interval. And again, I'm continuous on this entire domain of open 4, closed, open negative 1, closed 4. Now let's break out and see what we have for our absolute maximum. So it looks like this goes on forever up to infinity, which is not a point. So that is not going to be a maximum. So on this function, it looks like I have no absolute max. But I do have a smallest value. My absolute min is here at the endpoint at f of 4 equals 1. Now this smooth transition gives me no local mins or maxes. So it's really important to note that the local mins have to be inside, and the absolutes can include the endpoints. The absolutes can also be inside the interval, but they can include the endpoints. Locals cannot. So before you listen to this one, I hope that you can try this one on your own now that you've seen several. So take a few minutes, pause the video, and try and do the domain where is it continuous, the absolute values, and the local extrema. So my domain for this, again, you can see an asymptote here at x equals 0. So we're going to have an open 0. And it looks like we also go to e, and we have an open e. E is a value, just like pi has a value. The e is about 2.6, so that's why it's close to 3. And again, we're continuous on this entire domain. Now, we don't have a maximum value and we don't have a minimum value because we go down forever to negative infinity this way. So I don't have a minimum, and I don't have a maximum because that's not a closed endpoint. So I know I get really close to my largest value, but I never actually touch a largest value. And the same is going to go for the local extrema. So we're going to have no absolute max or min and no local max or min. Again, I encourage you to pause this video and try and answer example 14 on your own. Let's start with the domain. Here we have a closed circle at 0. So we start at a closed interval of 0, and we travel all the way to 2, where we have an open circle. But then here again we have our closed circle that travels to 6. So 0 to 6 is my domain. Now, where is the function continuous? Well, we're continuous between 0 and 2, and then again from 2 to 6. Probably an easier way to say this is, where is the function continuous? You could say everywhere except x equals 2. That's probably the easiest way to say where it's continuous. Okay, now let's look at our absolute values. So we have an absolute max. This is our largest value, so our absolute max is at f of 2 equals 6. And our smallest value is here. Our absolute min is at f of 6 equals negative 2. Now let's think about our local min. Well, here we have a local min. That's the smallest value of any of the other values around it. So our local min is going to be f of 1 equals 0. Now we already know that our absolute max, or our global max, is at 2.6, but that's also our local max. We don't have another local max, so that's the only one we have. And since it's inside the interval, that counts as a local max. It's worthwhile to note that since the function's not continuous at 2, I don't have a derivative at 2. That's going to become important soon. All right, for example 15, we have our closed interval of negative 2 to positive 2, and we're continuous everywhere. So all real numbers except x equals 0. All right, let's find our absolute max. Here we're going to have 2. 3 is our biggest y value, and that happens at 2 places. So our absolute max is at f of negative 2 equals 3 and at f of 2 equals 3. Although we get very close to our y value being 0, it doesn't actually equal 0 because we have an open circle, so we do not have an absolute min. For our local min and our local max, we're going to take a look at this whole graph. So our smallest value, again, this looks like it could be a culprit, but we don't actually equal it, so we can't use that. But here, f of 0 equals 2 is the largest value around it. So that's our local max. So I know we've done the intermediate value theorem, the mean value theorem, and now we're about to do the extreme value theorem. This is the third in our series of the value theorems that we spoke about before. If a function f is continuous on a closed interval ab, then f has an absolute max and an absolute min on that interval a to b. The important part here is that it must be closed. This is very important. And I want you to take a look back and see we didn't have an absolute max and an absolute min on every one of the previous figures that we went through on the last 6 slides. That's because not all of them were on closed intervals. Some of them were on open intervals. For example, if you look back, we had open interval on figure 11 and figure 12 and figure 13. So those don't have an absolute max or an absolute min. However, if we look at figure 15, it's on a closed interval, but it didn't have an absolute min. The reason that happened is it's not continuous. So that's the second part of this theorem that's really important. We had that open dot. That was the one that looked like this. So since it wasn't continuous at that x equals 0, the extreme value theorem didn't apply. And the same thing is true for 14. We didn't have a continuous function throughout the entire closed interval. So let's look at the condition for a local min or a local max. If f has a local min or a local max at a number c, then f prime of c equals 0 or f prime of c does not exist. This is super important. We're going to keep using this over and over and over. The derivative equals 0 or the derivative does not exist. That's how I find my local mins or local maxes that we're going to be start calling critical values soon. So let's do a little proof about why this works. So if we have a local max, that means that f of c is greater than or equal to f of x for some x on the open interval. So I can rewrite that as f of x minus f of c is less than or equal to 0. Now I know that the derivative f prime of c is equal to the limit as x goes to c of f of x minus f of c all over x minus c, which also means if this limit exists, then I have my limit as x goes to c from the left of f of x minus f of c over x minus c is going to equal the limit as x goes to c from the right, f of x minus f of c all over x minus c. So if x is less than c, and I have that f of x minus f of c is less than or equal to 0, then f of x minus f of c all over x minus c is greater than or equal to 0. And therefore my limit from the left as x goes to c of f of x minus f of c all over x minus c is also greater than or equal to 0. And the same thing holds true for the right side, except for this time we have the limit as x goes to c from the right of f of x minus f of c over x minus c is less than or equal to 0. And since I know that the limit from the left and the limit from the right must approach the same number in order for the limit to exist, then they both must approach 0. Thus, the derivative is equal to 0. And that leads us to this theorem, that if a differentiable function has a local min or a local max at c, then f prime of c equals 0. Now where this derivative is either equal to 0 or does not exist, this is called a critical number. As I said, these are going to become really important soon, and we're going to start talking more and more about those. All right, let's take a look and find our critical numbers here. Again, remember, our critical numbers are when our derivative equals 0 or our derivative does not exist. So we're looking for both of those situations to happen. So first, let's find our derivative. 3x squared minus 12x plus 9. Let's factor a 3 out. X squared minus 4x plus 3. And we're going to set this equal to 0. So we find our derivative, we set the derivative equal to 0. So again, we're going to factor. We get x minus 3 and x minus 1. We set that equal to 0, and that happens when x equals 3 and x equals 1. So I have two critical numbers in this case for this equation, and those are x equals 3 and x equals 1. Now here, I'm going to find my derivative equals 0 as well. So you know the chain rule. I prefer to use the chain rule. You can use the quotient rule. Whatever you want to use to find it is fine with me. So my derivative, negative 1 times x minus 2 to the negative 2, and then times the derivative of x minus 2, which is just 1. So negative 1 over x minus 2 squared. Now, when does this derivative equal 0? Well, that happens when my numerator is 0. So that doesn't happen because negative 1 doesn't equal 0. But when the derivative does not exist, that's when my denominator equals 0. So let's set that equal and see when that happens. X minus 2 squared equals 0. That's going to occur when x equals 2. So my one critical value here is when x equals 2. All right, let's look at the next one, part C. I'm going to do a u and a v for this. So my u is x minus 2 to the 2/3, and my v is x. So my derivative is 2/3, I'm going to write it as 2x times 3 cubed root of x minus 2 minus x minus 2 to the 2/3 all over x squared. So before I can find my critical values, I'm going to need to clean this up a bit. So let's make a common denominator. Right now we're over 1 here. So if I multiply by my common denominator of 3 times the cubed root of x minus 2, and I'm going to write it a little bit differently here. I'm going to write x minus 2 to the 1/3 because I think that will help you see how it's going to combine. So now that I have a common denominator, I have 2x minus, and x minus 2 to the 2/3 times x minus 2 to the 1/3 is just x minus 2 to the 3/3, or x minus 2. All over, I'm going to pull the x squared up, so I have 3x squared times the cubed root of x minus 2. And we'll distribute and then simplify, so I have 2x minus 3x, or minus x, and plus 6 all over 3x squared times the cubed root of x minus 2. So now I'm going to set this equal to 0, and I want to know when it doesn't exist. So I'll look at my numerator. When does negative x plus 6 equal 0? Well, that happens when x is 6. And then when does x squared 3x squared times the cubed root of x minus 2 equal to 0. Well, let's take each one separately. That happens when 3x squared equals 0, or the cubed root of x minus 2 equals 0. So that's when x is 0, or x is 2. So I'm going to have three critical values here: x equals 0, x equals 2, and x equals 6. Now when I look back at the original equation, g of x equals x minus 2 to the 2/3 over x. I know that my x cannot equal 0 because that 0 is not in my domain. That would make my denominator equal to 0, which means I'm going to throw this critical number away. So I only get two critical numbers in the end. That's why we've been focusing on the continuity and on the domains in the previous in 4.1, because this continues to be important, so we always need to be cognizant of it. Let's do part D on an additional slide. We don't have much room here. So again, our first step is to find the derivative. So g prime of x is cosine x. So I'm going to graph this because that helps me remember what I do. Cosine starts at 1, 0, negative 1, 0, 1. And then it just continues. So let's see, this happens at pi over 2, and at 3 pi over 2. Now, our domain is not bound here, so it's going to continue, which means it's going to happen at plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, plus or minus 7 pi over 2, and it's just going to keep occurring. So those are all of my critical numbers. Now when we're talking about absolute max and absolute mins, or the extreme values, the global extreme values. Again, I'm going to read you this theorem and then we're going to talk about what it means. Let f be a function that is continuous on the closed interval a to b, then the absolute maximum value or the absolute minimum value of f are the largest and the smallest values, respectively. So the value of f at the critical numbers on the open interval and f of b and f of a, the values at the endpoints. So to find our global max and mins, we have to find our critical numbers and find the y values of those, and then we also have to find the y values of our endpoints. So we have an additional extra step here. Before we do an example about finding the absolute extreme values, let's look at all the steps. Our first step is going to be, first, before we do anything, we have to confirm that it's continuous on the closed interval. Then we locate the critical numbers, as we were doing in the previous couple slides. Then we find the y values of those critical numbers and the y values at the endpoints. Then we look at the largest and the smallest. And I just like to do that with an xy table. So now let's do an example, and I think this will start to make a lot more sense. So in example 3 on page 294, it's asking me to find the absolute minimum and the absolute maximum for each of the value functions. So f of x equals x cubed minus 6x squared plus 9x plus 2 on the closed interval 0, 2. It's definitely continuous. I don't have anything worrying me about continuity, such as square roots or fractions. So we're good there, and we have our closed interval of 0 to 2. So let's first find our derivative. F prime of x is going to be 3x squared minus 12x plus 9, and we set our derivative equal to 0. And we already factored this one before, so we're good. X minus 3 and x minus 1. So our critical values are 3 and 1. Now to find our absolute minimum and absolute maximum, we're going to make an xy table. We always put them in order. So 0, 1, 2. And see how 3 is outside? It's outside of our closed interval, so we're not even going to use it. We're throwing 3 away. So now let's find f of 0. So I plug back into the original equation. I'm going to write the original equation right here so I don't forget what it is. So 0 squared minus 6 times 0 plus 9 times 0 plus 2. So f of 0 is just 2. F of 1, let's see, 1 cubed minus 6 times 1 squared plus 9 times 1 plus 2 is 6. And then same thing for 2. 2 squared minus 2 cubed minus 6 times 2 squared plus 9 times 2 plus 2. I'm just going to put this right in my calculator. Is 4. So now I see who's my minimum. My smallest value here is 2, and my largest value here is 6. So my absolute max is f of 1 equals 6, and my absolute min is f of 0 equals 2. So sometimes it wants to know the x value, sometimes it wants to know the y value, and if you don't answer it exactly the way they want you to on the AP test, you're going to lose some points. So I always answer it this way. So I give it in function notation, I give your x value and your y value, so I don't get caught not answering the question exactly as they want me to. Example 3 on page 294 again has a part B. And again, we've already done the derivative for this one. So I'm just going to use the derivative that we've already done previously. That was g prime of x equals negative 6 plus x over 3x times the cubed root of x minus 2. And again, I've solved my critical numbers here, and my critical numbers were at x equals 6 and at x equals 2. And remember, we had an additional critical number at x was 0, but we threw it away because it does not exist within the domain. All right, so we're going to make our xy table. Now this is worth noting that in a case specifically just like this, I would put the f of x value, or g of x, I guess I should say that I'm making an xy table using a g of x, not f. I would put this into my y equals in my calculator and then use my trace button to solve. So if you're having trouble understanding what I'm talking about there, that's definitely something we want to chat about in class. So by letting the calculator do all the work, I save myself a ton of time. So when x is 1, my y is 1. When x is 2, my y is 0. When x is 6, my y is 0.4199. And when x is 10, my y is 0.4. So we're looking for our minimum and our maximum. And it looks like right here we have our maximum value at 1, 1 and our minimum value at 0, 2. So I have an absolute max at f of 1 equals 1 and an absolute min at f of 2 equals 0. So on example 4 on page 294 tells us to find the absolute min and the absolute max for the function below. When x is between 0 and 2, we get 2x minus 1, and when x is between 2 and 3, we have x squared minus 5x plus 9. Before we do anything, we have to confirm that it's continuous on the closed interval. So let's take a look at the limit as x goes to 2 from the left, and that's going to be the first equation, the limit as x goes to 2 from the left of 2x minus 1, which is 2 times 2 or 4 minus 1, 3. And let's look at the limit as x goes to 2 from the right of the function. Again, that's the second equation. So the limit as x goes to 2 from the right of x squared minus 5x plus 9. So 2 squared minus 5 times 2 plus 9, which is also 3. So in fact, our function is continuous on this closed interval. So now that we've settled down on the continuity, let's decide about our critical numbers. So we're still going to take our derivative and set our derivative equal to 0 and when our derivative doesn't exist. So we have two different groups of derivatives to take. Our first one is going to be just 2. And that's on the open interval of 0, 2. So since 2 doesn't equal 0, we don't have any critical values from 2x minus 1. But let's do the derivative of the second equation. That's 2x minus 5. We'll set that equal to 0, and we get x is 5 halves. So my critical values from 2 to 3 is at 2.5. Now we have to look at when x equals 2. We're going to have to look at our one-sided derivatives. So let's look at the left-hand side of the derivative. Now I've already found the derivative of the left, which was just 2. So when f prime equals 2, my derivative is 2. So from the left, as x approaches 2, my derivative is 2. Let's look at from the right. As x approaches 2, we're going to have 2 times 2 minus 5 is negative 1. So my derivative from the left is not the same as my derivative from the right. That means that x equals 2 is a critical number because my derivative at 2 does not exist. That's a really important concept that we need to pay attention to here. F prime of 2 does not exist because the limit as x goes to 2 from the left of f of x minus f of 2 all over x minus 2 does not equal the limit as x goes to 2 from the right of f of x minus f of 2 all over x minus 2. So we have two critical values and 2 endpoints to look at. So let's take a look. 0, 2, 5 over 2, and 3. So when x is 0, I plug it into the first equation, I get negative 1. When x is 2, I've already plugged into both equations to see that it's continuous there, so my x is going to be 3. When x is 2.5 and when x is 3, I'm plugging those into my second equations. And I get 2.75 and 3. So this is a unique situation. We haven't had this yet. I have two absolute maxes because they both equal 3. And then here I have one absolute min. So my absolute max is going to be at f of 2 equals 3 and f of 3 equals 3. And my absolute min is at f of 0 equals 1. Example 5 on page 295. A rain gutter is being constructed by a piece of aluminum 12 inches wide. After making a length of 4 inches from each, the piece of aluminum is bent at an angle of theta. The area A of the cross-section of the opening expressed as a function of theta is A of theta equals 16 times sine times cosine of theta plus 1. And this is bound between 0 and pi over 2. And we're being asked to find the angle theta to maximize the area. So we're looking for our global max. And we can graph it and confirm that our A of theta is continuous on the interval 0 to pi over 2. So our next step is to find the critical value. So it's a u and a v. I'm going to separate we're going to use the product rule. So my u is 16 sine theta, and my v is cosine theta plus 1. So my u prime is 16 cosine theta, and my v prime is negative sine theta. All right, so a prime of theta is 16 cosine theta times cosine theta plus 1 minus 16 sine squared theta. So right now this looks really complicated, but let's do a little bit of distribution and see what works out. So I have 16 cosine squared theta plus 16 cosine theta minus 16 sine squared theta. So as you notice, I have almost sine squared plus cosine squared, but I have minus instead. So let's take a look at this sine squared. Hopefully remember Pythagorean identity of sine squared plus cosine squared equals 1. Well, I can't use that explicitly right now, but what I do know is sine squared is 1 minus cosine squared theta. So let's use that. We're going to substitute that in for sine squared. So now I have 16 cosine squared theta plus 16 cosine theta minus 16 times 1 minus cosine squared theta. And again, let's distribute my 16. And I have two 16 cosine squared thetas that we're going to combine. Let's continue this solution on the next page. So while this problem looks really intimidating, what if it looked like this? I don't think you'd have any trouble here factoring out a 16, and then you'd have 2x plus x minus 1. And I think you could factor this. I don't think you'd have trouble with that. So we'd get x is 1/2 and x is negative 1. We're going to use this exact same principle, but apply it to our cosines. So first thing we'll do is factor out our 16, and we get 2 cosine squared theta plus cosine theta minus 1 equals 0. And again, we're just factoring. So 2 cosine theta minus 1 times cosine theta plus 1. And that equals 0. So just like we did when we had just x's, we're going to set each piece equal to 0 now. So of course 16 doesn't equal 0, so we just ignore it. 2 cosine theta minus 1 is 0, and cosine theta plus 1 is 0. So let's solve, and we get cosine theta equals 1/2, and cosine theta equals -1. So here we need to know about our unit circle. When does cosine of theta equal 1/2? So in the first quadrant, because we're only looking at between 0 and pi over 2, when is my x value 1/2? Well, that happens when theta is pi over 3. Cosine of theta equals 1/2 also at 5 pi over 3. Now, when does cosine of theta equal -1? Again, you're going to look at your unit circle, and you get when theta is pi. On the AP exam, it's not likely that you're going to have the luxury of having your unit circle, so we really need to dedicate some time to memorizing that unit circle, or else these problems, although not difficult, become completely unattainable. Now, we were bound on our closed interval between 0 and pi over 2. So that means we're going to throw away 5 pi over 3 and pi, and we're only going to get one critical value. So let's make our xy table. We have 0, pi over 3, and pi over 2. All right, so let's plug in our critical values. We have 16 sine of 0 times cosine of 0 plus 1. Well, sine of 0 is 0, so this whole thing becomes 0. Let's take a look at pi of 3. 16 times sine of pi of 3 times cosine of pi of 3 plus 1. So sine of pi over 3 is my y value at pi over 3, so 16 times square root of 3 over 2. And my cosine of pi over 3 is 1/2, and that's going to be plus 1. So let's simplify this to be, to 12 root 3. And then for pi over 2, we have 16 sine of pi over 2, and then cosine of pi over 2 plus 1. Sine of pi over 2 is 1, and cosine of pi over 2 is 0. So that's going to be just 16. So while 12 root 3 looks kind of uncomparable to 16, this is about 20.78. So that's going to be our absolute max. At a of pi over 3 is 12 root 3. So now let's go back and take a look at the question again. The question asked us to find the angle theta that maximizes the area A. So we want to make sure we answer the question. So the angle theta that's going to maximize the area is when theta is pi over 3.